Welcome back to the workshop for one last video on section 3.5, multivariate distributions. In this video, we want to take a look at an example for computing a probability where there are three continuous random variables involved. So we have a joint probability density for three random continuous random variables. All right, so our density function is given by 1/3 of 2x plus 3y plus z, where x is between 0 and 1, y is between 0 and 1, and z is between 0 and 1. So we're no longer looking at the unit square. Rather, what we're actually looking at is the unit cube. So it's a little bit more difficult to observe this in a nice image because we have function values assigned to these locations. So I can't take that location and then demonstrate its function value at the same time. When I have a function defined on the xy plane, I can talk about the height away from that plane being the function value. But here, I would have to introduce a fourth dimension to talk about the distance away or the height away from this any location in the cube. So it's a little bit different. So we don't have the nice visualizations, but the concepts extend seamlessly to three or four variables or three or more variables from what we had in two variables, and that the integration concepts are exactly the same. So if I want to find the probability that x is less than 1/2, formally, this is the probability that x is less than 1/2, which can be calculated as the integral from. Now, since it doesn't matter what y value or z value is taken on here, I can integrate from -infinity to +infinity for z, and I can integrate from -infinity to +infinity for y, and then integrate from -infinity all the way up to 1/2 for x, because that's the one I'm actually interested in. So for that, we would integrate the function x, f of x, y, z. Integrate with respect to x, then y, then z. And in this case, right, I don't have to worry about a majority of this very large region. Okay, I really don't have to worry about it because it's 0 outside of the unit cube. So in terms of z, I only need to integrate from 0 to 1. In terms of y, I only need to integrate from 0 to 1 because it's 0 outside of that. And then for x, of course, I don't need anything below 0, so I go from 0 to 1/2. And now that I'm looking at the region where the function is defined to be non-zero, and it specifically takes on this one expression, I can integrate that. 1/2 of 2x plus 3y plus z dx dy dz. Now, if you wanted to, you could go through and perform each of these three integrations, and that would be absolutely fine. I don't think anyone would tell you not to. But what we can do is we can go ahead and compute these in Mathematica or whatever program you find best. Again, Mathematica should be available on the university computers, so you should be able to visit the library or a computer room and be able to access Mathematica. If you're not finding that, let me know, and I'll double check on where exactly we can find computers with Mathematica. So we have to perform with three integrations. So I'm just going to type it all in at once this time. So my outermost integration is the integration with respect to z. So I write that one first. But before I can integrate with respect to z, I have to integrate with respect to y. But before I can integrate with respect to y, I have to integrate with respect to x. And what function am I integrating? Well, I'm integrating 1/3. Ooh, yes, I may have copied that wrong in my notes. Let me just double check that a moment. Yep, This is a 1/3 coefficient here, and here I wrote 1/2, so that's supposed to be 1/3 there. My apologies. So we go back to Wolfram alpha. So 1/3 times, we have 2x, 2 times x, plus 3 times y, plus 3 times y. Let's see here, plus z. Let's see here, plus z. Plus z. There we go. All right. So that is what we are integrating, and our first integration is with respect to x, and we are integrating from 0 to 1/2. That concludes our first integration. Our second integration is of that integral, and we are integrating with respect to y. Oh, make sure we include a comma there. Integrate with respect to y, and we are integrating from 0 to 1. That concludes our second integration, and then our third integration is of that thing that we just found, and we are integrating with respect to z, and we are integrating from 0 to 1. That's our third integration. So we get all of that typed in, and then we hit enter, shift enter, and it gives us our calculation, 5/2. I would like to point out here, if you were to use 0.5 instead of 1/2, 0.5, it will give your answer. It'll give the answer as a decimal as well. Okay, so if you want to have the nice fractional answers, which are preferred, of course, then you would want to make sure that you are using fractions in your integration bounds. All right, so 5/2. And we used Mathematica for that. If you want to use Mathematica for your calculations, that would be fine for the most part. I do want you to be capable of making those computations as well. So I would like you to be prepared as best as you can on an exam to see in the directions to complete a particular integration by hand. But if it doesn't specify that, then you're welcome to jump from here to here. But you should specify how you found that integral. If you're not doing it by hand here, you should say, "Hey, I used Mathematica." Excellent, cool. Or you used GeoGebra, whatever you happen to find that works. So this is the probability that x is less than 1/2. Of course, I copied the number wrong. 5/12. There we go. So again, when we're talking about continuous random variables, we are extending things in exactly the same way. If we want to know if a function can serve as a joint probability density function, then we would simply have to make sure that all of its values are non-negative and that the integral over the entire three space or three-dimensional region. Okay, we want to make sure that that integral is equal to 1. The area there is 1. Area, volume, kind of weird there because we're talking about essentially 4 dimensions. But we want that, and then for the cumulative probability distribution, cumulative joint probability distribution, if we're talking about the probability that x is less than or equal to x, right, f of x, y, z, y is less than or equal to y, and z is less than or equal to z, it would be the integrations from -infinity to z, -infinity to y, -infinity to x, f of s t u ds dt du. Okay, so it extends the same way that it did from 1 variables to 2 variables, here to 3 and 4 or more. Okay, so it's all the same idea. All right, but that's all that I got for you guys for section 3.5. Yay, way too many videos for this section. I feel like I agree with that statement if that's what you're saying. So thank you for your time and your patience. I really do appreciate it. You guys have yourself a great day, and I'll see you back in the workshop very soon.